So now let's do some real world problems. Right? So physical science. The table below shows the relationship between the number of seconds y it takes to hear the thunder after a lightning strike and the distance x you are from the lightning. Right? So the distance is the independent variable, and the time in seconds is the dependent variable. So here's one of the times where time is the dependent variable. And that's because we're looking at how long something takes. And how long something takes, in this case, how long it takes to hear the thunder, depends on how far away the lightning is. Right? So the time it takes to hear the thunder is as a function of how far you are away from the lightning. All right, so now let's graph the data. All right, so we have the point 0, 0. So I'm going to graph in green. 0, 0. And no negatives, right, because there's not negative time or negative distance. And then, before we do anything else, let's put some values on this. All right, so I'm not going to use the same scale on the x and the y. The x's can go up by 1 each time, right, because these numbers are pretty small. And the y's, let's have them go up by 5. Right? So for the x's, each box is going to be 5. For the y's, for the x's, each box is 1. For the y's, each box is 5. Right? And I don't like to usually use different scales on the x and y, but if I don't, it'll never fit. All right, so now let's graph it. All right, so, and as long as I'm consistent, I can still find the slope. All right, so we have one scale for the x's, one scale for the y. All right, so now we have the point 1, 5, and then we have the point 2, 10, and 3, 15, and 4, 20, and 5, 25. And so even though we change the scale, we can still see that this is a linear function, right, because it has a constant rate of change. Now, if we said the constant rate of change is 1, because it goes up 1 to the right 1, well, then we are wrong, right, because the scale on the y is not 1. Let's calculate out using the slope formula, which is the same as average rate of change. And that is the change in y over the change in x. All right, so it doesn't matter. As we can see, we have a constant rate of change, so it doesn't matter which values we choose. All right, why don't we choose the 0, 0, and 1, 5? All right, so we're going to take the change in the x values. Oops. I meant to put change in the value of the function. I swear I have distance formula trapped in my head now. So change in the values of the function divided by the change in x. All right, and so here's our x values. Right? And you know what? Let's use the larger number first, because we see it's got a positive slope. All right, so ubx2 and ubx1. All right, and of course this would be f of x2, what we get when we plug 1 in, and this was f of x1. So that gives us 5 minus 0 over 1 minus 0, and that's a slope of 5 over 1, or 5. All right, so now let's put some units on this. All right, it is a unit rate, and it's in context, so we should have units. All right, so it takes 5 seconds, because it's the dependent over the independent. 5 seconds. I do not see what the unit of measure is on the distance there. Let's call it, I think it's miles. So 5 seconds per mile. It's not like you'd be 1 foot away from the lightning, or you'd have some serious problems. So for every 5 seconds, between a lightning flash and the sound of thunder, there is 1 mile between you and the lightning strike. And there we go. All right, so here we looked at average rate of change with the linear function. Let's see about the other two. Are they linear? Are they non-linear? And I think this is the last one. Nope, 2. And that's not linear, right? And let's see about this one. At 1 p.m., the water level in a pool is 13 inches. At 2:30, the water level is 28 inches. What is the average rate of change? Right, so remember that average rate of change is the difference in the value of the function divided by the x values. You can also consider it to be the change in y over the change in x. Now, the y values, this is our dependent values, dependent variable. So the dependent variables in the numerator, the independent variables in the denominator. And so the dependent variable is the water level, and the independent variable is time. Right? The water level depends on how long the hose is in the water. Right? Now, something to note, because sometimes students mess up time, and the reason is because it doesn't keep going up, right? It goes around in circles. So it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then back to 1 again. Right? So other numbers don't do that. So for time, find elapsed time rather than subtracting hours. And then you don't have to worry about when it goes past 12. So here, the elapsed time is how much time it is from 1 p.m. to 2:30 p.m. Right? Well, that would be 1.5 or 3/2 hours. All right, so now we're just going to divide either by 1.5 or by 3/2. All right, and we don't have to worry about subtracting. We don't have to worry about this. All right, so we'll do that when we have elapsed time. All right, when we have time and we're looking at time on a clock, not two different not just difference in x values, but difference in time, and that just because time keeps repeating itself. All right, so we're going to take the difference in the heights of the water. Now squeeze it down here. All right, so our ending time so far is 28 inches. So the later time, it was at 2:30, it was 28 inches. At 1 o'clock, it was 13 inches. And that's 1.5 or 3/2 hours. All right, so 28 minus 13 is 15 divided by 3/2. And dividing by 3/2 is the same as multiplying by 2/3. All right, so we can reduce. 3 divided by 3 is 1. 15 divided by 3 is 5. And 5 times 2 is 10. Let's interpret that. So it's 10 inches per hour. All right. If we wanted inches per minute, then we'd have to divide that by 60 because there's 60 minutes in an hour. All right. So average rate of change is just the slope of the secant line connecting the points, and it's always the dependent variable over the independent variable. And then for time, use elapsed time, and then you don't have to worry about the hours repeating again. All right, so here's this one. One last problem. This is a very nonlinear problem. The graph below shows the fluctuations in the price of a stock over the course of the day. Find the average rate of change of the stock's price between 8 a.m. and 2 p.m. All right, so here's a very good example about elapsed time. Right, you wouldn't want to do 8 minus 2, right, and say that's 6, all right, necessarily. It'll work that way, but if you did, so it's just easier for these if you just figure out elapsed time, all right, and then you don't have to worry. So for instance, the difference between 9 a.m. and 1 p.m. is not 8 hours, all right, so just figure out elapsed time. All right, so for the first one, the elapsed time, all right, so we've got 4 hours to go from 8 a.m. to 12 p.m., and then 2 more hours, so that one is 6 hours. And it even gets more complicated. We got to figure out a.m., p.m. So this just makes it easy. 9 to we'll figure out both elapsed hours. 9 to 1. So from 9 to 12 is 3 hours plus 1 more is 4 hours. So here the elapsed time is 4 hours. So you can see it really wouldn't be good to subtract 1 from 9. All right, so now let's just do the average rate of change, and we'll number this one 1 and this one 2. So for 1, all right, so the average rate of change is going to be change in price over the time, the elapsed time. All right, so now let's look at some mark, because we looked at how much time has gone by, but not the price of the stock. So 8 a.m. looks like that point is here. So it looks like that at 8 a.m. the price of the stock is $5. And then at 2 p.m., all right, so 2 p.m. looks like it's halfway in between 13 and 14, so $13.50. All right, so that would be $13.50 minus 5 divided by 6 hours. All right, and we'll put this in terms of dollars and cents. So that would be $8.50 divided by 6, which is $1, and we'll round to the nearest cent, $1.42 per hour. Right, so that's the average change in the price of the stock, and it went up if we consider this point and this point. Right? Now, if we choose 2 other points, right, so essentially it's this. If we choose 2 other points, right, it may not be positive. All right, let's find one last one, number 2. All right, so average rate of change. So change in price over elapsed time. Squeeze that in there. All right, so we're looking at 9 a.m. So we have to estimate that a little bit. That looks like maybe halfway in between 6 and 7. So let's call that 9 a.m. 6:50. And then at 1 p.m., I guess that's halfway between 6 and 7. So 1 p.m., 6:50. So we're finding the slope of that line. All right, so we had to estimate a little bit. Let's see what we get. All right, well, the change in price would be 650 minus 650 over 4 hours. Well, that's just 0. So there was no change in price if those are the 2 points we look at. Right? So if those are the only two we're considering, the average rate of change is 0. Right? And so that's my last problem with average rate of change. So you see we've calculated it from word problems, from tables, from graphs, and from equations. So anytime you've got a function, you can calculate out the average rate of change. All right, so thanks for watching. Bye for now.